Hello Sim Pilots, welcome back to the cockpit of the Hind. We're on the wonderful Nevada Test and Training Range map, Nellis Air Force Base, the north-eastern side of the field on one of the helicopter pads surrounded by windsocks. Why are we surrounded by windsocks? I have been asked to do a video on why people are going round and round in the Hind, especially at high gross weights. So at the moment we've got about a 2 metre per second wind coming off the nose of the aircraft, and I've sort of configured my cockpit instruments to reflect the direction of the wind. I am at maximum takeoff weight, so 75% fuel. I've got 2 sets of spiral 2s, one on each wing, and if we look outside the aircraft, I've got a set of rocket pods as well. That is maximum takeoff weight for the Hind, so if you're loading the aircraft up above that, then you're already overtaxing the helicopter. So, things to remember, things to think about with the Hind. The Hind has a clockwise turning rotor system, which is unique from the Apache, which has an anti-clockwise turning rotor system. What does this mean? Well, as a pilot, as we look at the rotor disc, and it's probably very difficult to see at the moment, but it's spinning from left to right, in my view. That's going to want to make the nose of the aircraft go from right to left, so it's going to want to make the nose yaw to the left due to the torque generated by the engines keeping that rotor disc spinning. The more power we add to the aircraft, the more left-hand yaw we're going to get, more left-hand rotation we're going to get from the aircraft. Okay, it's basic physics. This matters because the aircraft only has a limited amount of power. So the more power you apply, the more left yaw motion you're going to get, the more anti-torque you're going to have to apply using the pedals in order to correct that issue. So we all know about the main rotor disc. It's sat there in its horizontal axis spinning away, producing torque. The tail rotor mounted on the boom at the back end of the aircraft is essentially a main rotor disc that's been rotated through 90 degrees and bolted onto the back end of the aircraft. Whereas the main rotor has both collective and cyclic pitch, the tail rotor only has collective pitch. And by moving the pedals, you are essentially changing the collective pitch of the blades to request a bigger or smaller bite of the air being taken by those blades. This matters because the tail rotor behaves a lot like the main rotor disc in certain areas of flight, and especially in the hover, and it interacts with the main rotor disc in combination with the wind to produce some effects. Now you may or may not have heard of something called the power pedal. This refers to, in the Hind, the application of right hand pedal, so right hand yaw. Okay. If I bring the aircraft into a hover and I want to turn left, what I'm essentially asking the aircraft to do is let the torque of the main rotor spin the aircraft to the left. So if I apply left boot, the tail rotor takes a smaller bite of the air and allows the nose of the aircraft to rotate round to the left. Great, we're working with the aircraft at that point, you may think. If I ask for right yaw, or right rotation, I'm going to apply right pedal. It's going to command the tail rotor to take a bigger bite of the air, and it's going to pull my aircraft round to the right against the action of the main rotors. So on the face of it, why don't we always turn left? The engine's trying to turn us that way, torque's trying to turn us that way anyway. Surely that's a free lunch. You'd think so. And in a certain case, if you want to turn left, then that's right. That's fine. The problem comes when you want to stop turning left. So it's always good to remember that it takes more power to stop a turn than it does to start a turn when we're going left. So if I give left boot, the aircraft starts to turn left, the tail rotor's taking less a bite of the air, we start the turn. If I then want to stop the turn, I have to apply right boot to stop the turn. The tail rotor's then got to take a big bite of the air, because it's not only got to apply the force it was applying to keep the aircraft stable in the first place, it's now got to apply more force to arrest that rate of turn that we've just started, which you can see could be a problem, because at high gross weights we're already demanding a lot from the engines in the first place, bearing in mind that the tail rotor's powered off the main engines. We may come into a situation where we don't either have the power available or the tail rotor authority available to effect that manoeuvre, and that's why we see people going round and round, usually in a clockwise direction. It's worth remembering that when you're asking things with the tail rotor, that power has to come from somewhere. We just spoke about it coming from the main engines. What will usually happen is, when you command right pedal from this aircraft, the immediate power that's going to come to effect that manoeuvre is going to come from the main rotor disc. It's like a flywheel. So what happens is, it's a power demand, the rotor system responds instantly, and the engines take time to catch up to replenish that level of power. If your engines are already in an overtaxed state, trying to keep you in the air because you're at max gross weight, then they can be overwhelmed by the power demand placed upon them, and you can start to sink because your main rotor RPM starts to dip. And at that point you're in a real world of problems, because not only are you turning left without the power to bring the aircraft back to a stop, but you're also running out of main rotor RPM as well, which can cause you to corkscrew into the ground. So what about this power pedal? We try and turn in the hover on the power pedal because we're demanding more power from the engine to do that, so there's a limit to the amount of turn, rate of turn, or the amount of power authority that we can get out of the aircraft. We're going to hit that limit before we hopefully hit the tail rotor effectiveness limit of the aircraft. There are some things that can affect the amount of tail rotor authority you've got. So if we look off the nose now, the wind's coming directly off the nose. We're happy in this because that's aerodynamically very comfortable for the aircraft to deal with. You've got, if we look outside, a long, slender aircraft compared to the wind, and all these control surfaces that are going to keep the aircraft stable when it's facing into the wind. If we start to look at various things that can cause us problems now, if we're going to hover with our tail into the wind, we can have something that's called weather vaning or weather cocking, which is, if you've ever seen the top of a church or an old building with like a rooster or a cockerel on top, a little old style weather vane, it's the same principle. The tail of the aircraft is going to want to spin round and flow with the wind. Okay, so it's going to want to always point the nose of the aircraft back into the wind again. This can be quite useful, but not if you're trying to hover the aircraft with its tail into the wind. So you'll find yourself dancing on the pedals, trying to control that weather cocking, weather vaning. This is another thing where, unfortunately, in the sim you don't have the feel of what the aircraft's doing. So at some points during your turn you can find that you are dancing on the pedals and trying real hard to keep the aircraft stable, and it's generally because you're trying to hover with the tail close to the wind, and you'll generally find that to be an issue between about 150 and 240 degrees on the aircraft. So if I look at the HSI now, I'm heading into the wind, you know, 150 to 240, so in the back sort of third of the aircraft, if the wind's coming from that direction, you're going to feel those effects. We talked earlier about the tail rotor being just like a main rotor, and in that sense it acts with the same issues with VRS that the main rotor has in certain wind conditions. Because of the way it's drawing air into the tail, what we can get, if the wind's coming from about 30 degrees off the right hand side to about 150 degrees, so you're talking, you know, from over here to over back here somewhere, if the wind's coming from those directions, so if I'm trying to hover with the wind to my right, it can cause VRS conditions in the rotor disc, in the tail rotor disc, which is going to reduce the effectiveness of your tail rotor system, you know, loss of tail rotor effectiveness again. And finally, because of the way the blades interact with air, the main rotor discs interacting with the air, we can have vortices shed from the main rotor disc. You can't see them, but they're happening all the time. All around the disc, there's a big ring of vortices being shed from the tips of the main rotors. And when the wind is blowing from the right hand side, those vortices can be blown into the tail rotor, and basically you're getting turbulent, dirty air being blown into the tail rotor, and that's going to disrupt the amount of lift it can create. You know, turbulence is bad, it's not a clean airstream, it's going to cause issues for the helicopter. And that's going to be from about 45 degrees to about 75 degrees. So if we look out over here, if the wind's coming from this sort of direction over here, you're going to feel that turbulence, loss of tail rotor effectiveness on the aircraft. The best way of doing these things is to avoid the conditions that loss of tail rotor effectiveness occurs within. So the US National Transport Safety Board issued some guidelines a while back, and they indicated the issues that can affect airflow entering a tail rotor are operating at speeds below translational lift velocity, operating at high altitudes and high gross weights, operating near large buildings or ridge lines, that's due to the turbulent air that's coming off those structures, and relative wind direction. So that's a very quick rundown, and now you should be a little bit more aware of what's going on with the aircraft. So in summary, try not to operate the aircraft over its maximum gross weight. Try not to put the aircraft into conditions where the wind is coming from 45 degrees off the right hand side of the nose, is coming from the right hand side of the aircraft in that big arc, is coming from behind the aircraft, because that's going to cause your weather vaning effect. And always try to make pedal turns where you must with the right hand boot. So I'll show you that it is possible to get the aircraft off the ground in these conditions. First of all, as we talked before, set your initial trim position, and we're going to look to do as we did before, in that we are taking the wheel brakes off the aircraft, and then we're going to apply power to the aircraft slowly, and we're going to watch what the aircraft does. Retrim, power coming up, more and more pitch, there's a little bit of left roll there, so we can take that out, a little bit of movement again, take that out, feeding a bit more anti-torque pedal, and as you can see there's a lot of power, you know, eventually there's going to be a lot of power being used to get this aircraft off the ground. Okay, and we're up. So the most important thing to remember is any pedal turns you make, and I'm going to make one now, need to be slow. And when I say slow, I mean slow. So I'm going to move the nose around on the power pedal, keeping the aircraft centered in the pad. So using little bits of cyclic, moving the aircraft around very slowly, okay? We're not in a rush. The more you rush, the faster you try and do this, the more you're going to demand from the aircraft. You see we're starting to sink a little bit, so just add a little bit more collective pitch. The more you demand from the aircraft, the more issues you're going to have. Okay, so we're now at 90 degrees to the direction of the relative wind. Okay, and if we want to depart now, what we're going to do is we're going to increase power to maximum available, and then we're going to ask for forward cyclic. I'm going to start running the aircraft forward. Right, we are at max continuous now. Run the aircraft forward, and we're going to let the aircraft accelerate. Let her accelerate. Watch the instruments, make sure we're not sinking, watch the speed coming up, and there we go, through ETL, and the aircraft's away. See the vertical speed rising, see the speed rising. I'm feeding out anti-torque pedal because the airframe's taking over, that aerodynamics of the aircraft are taking over, and the aircraft's away. Okay? Retrim. Coming up to 150, raise the landing gear, and away you go. Hopefully that's given you a little bit more confidence with the aircraft in high gross weight situations, and hopefully giving you a bit of better understanding of how the tail rotor works. I'm not an expert, I'm not a pilot, I'm not an aerodynamicist. This is just from reading and experience and working with the Hind over several hundred hours. So I want to thank you for your time, wish you a safe flight, have a good day.